In the previous lecture, we had started the discussion on support vector machines and we saw the mathematical formulation. Specifically, we discussed and derived what is a margin or the distance, what is the distance between two parallel hyperplanes. We then use that derivation to figure out how do we maximize the margin, which is the goal of our SVM classification. And then we went on to look at both the primal and the dual form, right? And then we solved a couple of examples. We solved one example using both the primal and the dual form, and then we stopped at the point that can we use SVMs if the data is not linearly separable. Thus far the data that we'd seen had been linearly separable, and in such cases, in fact, even trivial classification techniques could work really well. But the real power of SVMs come into play when the data is non-linearly separable. So in this particular example, we have non-linearly separable data in the sense that you cannot draw a boundary and get you cannot draw a line, like you cannot draw a line like this or a line anywhere so that you'll be able to get a perfect classification. Thus the data is not separable in the existing dimensions. And the question then is that can we still use an SVM? And we can. The key idea is that we'll be projecting this data, which is now along a real numbered line, to a high dimensional space. And the hope is that in the high dimensional space, the data would be linearly separable. So that's mostly it to what we will be discussing in today's lecture. Here is the diagram again. The original data is along the real number line. I have now done a transformation, which is I've now projected the data to high dimensional space. So if you see, I have one dimension which is x, which is the same as before, and the other dimension which I have now, or which is now I've increased the dimension of added a feature, is x minus 1 the whole squared. So if we do this transformation, you'll see that the point which was earlier 0 will now be mapped to 0 comma 1, since 0 minus 1 whole squared is 1. The yellow point which was earlier 1 will now be mapped to x equal to 1 and x minus 1 whole square equal to 0. And similarly the point x equal to 2 would be mapped to x equal to 2 and x minus 1 whole square, the other feature is 1. And we look at the other color points also, which are the other class. So the x equal to 3 is mapped to x equal to 3 and x minus 1 whole square equal to 4, so on and so forth. So now if you see, now we have a transform data set which is in R2, and now you can trivially draw a line which can now separate out these two classes of examples. And what I've illustrated here is a max margin separating hyperplane, so exactly what we'd been doing earlier. Now an interesting thing is the original data is in R, we transformed it and we drew a hyperplane to separate out these classes. Can we take this hyperplane in the transform or the projected space and put it back and then see how the classification boundary looks like, right? So that's exactly what we are going to do now. So if you notice, this particular boundary looks like x minus 1 whole squared equal to something, right? In fact, that point, that something is the midway between y or x minus 1 whole squared equal to 1 and x minus 1 whole squared equal to 4. So between y equal to 1 and y equal to 4, the exact midpoint between that, which is 5 over 2. Thus we have x minus 1 whole squared equal to 5 over 2. So x minus 1 whole squared equal to 2.5 is my separating boundary or the separating hyperplane equation. I take it back again to the original dimension, and I can again write x minus 1 whole squared equal to 5 over 2, or I can write it at x minus 1 whole squared equal to root 5 over 2 the whole squared. Now this is an equation of a circle which is centered at x equal to 1 and has a radius of root 5 over 2. And if I draw the circle, now you can see that what we had previously, the data which was not separable in the original dimension, by drawing a linear classification boundary, we projected it to high dimension. But then if you take the hyperplane back to the low dimension, you will be able to separate it using a non-linear boundary, right? So that's essentially the idea of this lecture. And to give you an example of going from R2 to R3 space, consider this particular example where you basically see that there is an inner circle in which one of the class lies, and then there is an outer circle outside of beyond a certain radius that the other class resides. The original data is in R2. Now think of it that you're viewing this data in a three-dimensional space, and you apply some kind of a transformation where you pull up these purple points and the yellow points are pulled down or they remain as it is. And if you do this operation, or think of it as that you're viewing the contour of a particular ridge, and the innermost points are actually at higher altitude. That's exactly what we are looking at it in this particular R3 space. And then we can draw a hyperplane in the R3 space, which is going to be separating out these two classes of points. Again, you can take the separating hyperplane and you can project it down back again to the original dimension, which was R2, and it would be a circle in the R2 space. So that's how we can apply SVMs even on non-linearly separable data by projecting the data to a high dimension. So let's assume that the original dimension was small d, and the new transform dimension is capital D, where capital D can be anything greater than small d. In this case, in the previous two examples, we have been keeping capital D equal to small d plus 1, right? And in the first example, we had small d, the original data is in R1 or R, and the transform data is in R2, thus capital D equal to 2, right? Now let's get back to the maths again and try and understand that what is this projection operation going on, and can we do something to make these operations more efficient. So in a linear SVM, we were trying to maximize this particular quantity, which is I'm showing this in the dual form. You could have minimized the expression in the primal form, and that's essentially the same. Now you and of course you do this with respect to all the constraints being satisfied. And what you need to change in this equation in order to still be able to use the same linear SVM formulation is, as you've seen before, the data is transformed into a high dimensional space. So you use a function phi to transform. If you see in this equation, we use a function phi to project upwards or to transform of original data in R small d to the new data in R capital D. So that's the only thing which we change, and then we use the same exact linear SVM formulation. So it's a really cool trick through which you don't need to change the existing mathematics, or you can use the same implementation. Only you need to change xi's to phi of xi's and xj to phi of xj. So basically every xi is replaced by phi of xi. Now here is another example, and I would urge you to run this example on your own at your own time. This is the example which I run using sklearn, and previously when I had basically shown you different x minus 1 whole squared as the x minus 1 whole squared equal to root 5 by 2 squared as the decision boundary. In this case, in the SVM, in the sklearn polynomial kernel, we'll come to kernels. kernel that we use, this is another kind of a transformation that you can do on this original data. So the original data is x, which is in R1. The transform data is phi of x, where you create two features now. Those features are x1 and x2, where x1 is root 2x and x2 or y is x squared. So notice in the previous examples we were always retaining the original dimension. But in this case, we are not retaining the original dimension. We have sort of modified the original dimension into two new dimensions, root 2x and x squared. And again, we use the exact same formulation, and you can see that we can then draw a classification boundary, and we can then plot the support vectors. In this case, we see 3 support vectors, right? So we'll keep using this example 1 or 2 times more to understand this even better. So essentially, the steps that we have to follow in this particular formulation is that first we compute phi of x for each point, where phi is a transformation from r small d to r capital D. In the previous example, this transformation is root 2x and x squared. And then you compute the dot products over the r capital D space. So in case you have forgotten what the dot products were, if you remember, we had dot products between each pair of points in this expression. So between xi and xj, and the other terms in this expression are all scalars. Alpha I and alpha j are the Lagrangian multipliers for the corresponding constraints, and yi and yj are the corresponding labels for the points xi and xj. But we do a dot product between xi and xj, and instead of that, when we project it to high dimension, we now do a dot product between phi of xi and phi of xj. But the thing to note here is that oftentimes we'll be using capital D, which is much greater than D. If we do it that way, like if we choose a capital D in such a way, then computing phi of x for each point is an expensive operation, because we have to essentially compute all of these polynomial features. I leave it as an exercise for you to calculate the time complexity of this particular featureization. The second thing that you're doing, which is the dot product over the R capital D space, that is also an expensive operation, because earlier you were computing the dot products in a smaller dimensional space, small d, but now you're computing the dot products in a larger dimensional, capital D dimensional space. And I again leave it up to you to revise that what would be the time complexity of computing the dot product of a capital D dimensional of two capital D dimensional vectors. So since both of these steps are expensive, we would like to do something which can help us bypass these two limitations and reduce the time complexity, overall time complexity, while at the same time retaining the basic properties that we are after, so that there is some notion of projection to a high dimensional space and we can still do nonlinear classification that way. So it turns out that this is one of the most popular and interesting tricks in machine learning, and this particular trick is called the kernel trick. So the kernel word we have already seen in the lectures on Gaussian processes. The kernel functions or the kernel trick is essentially trying to show how we can efficiently compute the dot products or the similarity between pairs of points, right? The core idea in the kernel trick is that, so for the SVM formulation we need to compute this quantity, the dot product between phi of xi and phi of xj, right? So we say that, can we write a function k which operates on the inputs xi and xj, or the vectors xi and xj, such that this particular function is the same as the dot product of the transformation, right? So k xi xj is some function of the dot product or some function defining the similarity between xi and xj, because that's what dot product is supposed to do. But this particular function gives you the dot product in the high dimensional space after you, which is basically after the transformation. So it's interesting to see if we can find out such class of functions, such class of kernel functions. And it turns out that there are a lot of classes, there are a lot of variants of such functions, lot of types of such functions which exist, and they have to satisfy something known as a Mercer condition, MERCER condition. And if these kernels satisfy the Mercer condition, they are then valid kernels, and you can use them in for these computations. So now we look at some examples to understand the kernel trick better and appreciate why it's a really important contribution. Alright, so in this particular example, just a few minutes back, we saw transformation phi of x equal to root 2x and x squared. This is capital D equal to 2. The output is root 2x and x squared, and the original input was in R, which was x, right? So I'm going to argue that if we use this definition of the kernel function, so the kernel function is defined between a pair of points. Let's call these pair of points xi and xj, and I define the kernel function as 1 plus xi xj the whole squared minus 1, right? Where xi xj is the dot product in the lower dimensions. So we just expand this term out. Lower dimension means the original dimensions of xi xj. If we expand this thing out, and then we can basically see that this is 1 plus 2xi xj plus xi squared xj squared minus 1. This 1 and 1 gets cancelled out, and we can rewrite this entire thing as a dot product between a pair of vectors. The first vector contains only xi terms, and the second vector contains only xj terms. So the first term here is 2x1 xj. We can write that as the product of root 2 xi and root 2 xj, and the second term is xi squared xj squared, which can be written as the dot product of xi squared and xj squared, or the product of these two quantities, sorry. So essentially we can create these two vectors, root 2 xi squared and root 2 xj squared, whose dot product gives us this functional evaluation kxi xj. So both of these are equivalent, and we have just verified that this is basically the dot product of the projection of the projected vectors, right? Now let's go ahead and try and understand this even better. So the original data set is of this format. We have the sample numbers, we have x and y, and x is going from -2, then the class is -1. If the x is -1, the class is -1. If x is 0, the class is 1, so on and so forth. If we were not applying the kernel trick or the kernel function, what we would have to first do is to transform the data set. So if you remember, we had two features, root 2x and x squared. So we transform the data set and get a new data set which looks like the following: sample number root 2x. So for -2, root 2x is -2 root 2, and then the second feature is x squared, and the third feature is y. So you create a transform data set this way, and then for each pair of points which is required in the formulation. So in the formulation we need to do phi xi dot phi xj for each I and j for each pair of points. So let's pick up a couple of points. So we pick up the first sample and we pick up the second sample. So if we were to do phi xi dot phi xj, so phi of xi is -2 root 2 and 4 dot product with minus root 2 and 1. So -2 root 2 into minus root 2 is -4, is 4, and 4 into 1 is 8, and if you sum up these you'll get 8. So this is the dot product in 2D, but let's again do some computations. Let's again do some calculations as to number of computations required. So first we took this -2 and transformed this to root 2x, so that's one multiplication required. Then you did x was transformed to x squared. Again, another multiplication required, a squaring required, another arithmetic operation required. You do this for the second example also. So in total you have used up 4 such arithmetic trivial operations, and then you do dot product. So dot product would require minus 2 root 2 into minus root 2. So that's your fifth arithmetic operation. 4 into 1, that's the sixth arithmetic operation, and the sum of these, which is your seventh arithmetic operation. Right, so in total you have used 7 arithmetic operations, and this is just increasing the dimension by 1. But let's see if instead of using the transform dataset, we were to use the kernel function k. The kernel function that we have to use is kxi xj is equal to 1 plus xi xj the whole squared minus 1, right? So what we here need to do is to firstly the dot product, which is xi xj, is just computed between the original data, in this case which is a scalar. So it's a trivial 1 multiplication required. So 1 multiplication, 1 addition, 2 operations, squaring 3 operations, minus 1 4 operations. So in the first case, when we first did the transformation and then the dot product, we required 8 operations. In this case we require half the number of operations, and this is just going from small d equal to 1 to capital D equal to 2. If you go to a much higher dimensional space, the amount of calculations required would be huge. So this is how the kernel trick is really going to be very useful for us. And one of the main reasons why kernels become extremely useful over and above the calculation overhead or the computational overhead that we have discussed is that, one of the reasons why we were using the dual form was because of kernels. So we have identified that kernels can help you to significantly reduce the computational overhead, and the dual form is better suited to leverage the kernels or the kernel function. Can you pause for a minute, go back to your slides and compare the formulation for the primal and the dual form and convince yourself why this is the case, or why do kernels make sense in the dual form and not in the primal form. The simple idea is that the primal form does not allow for the kernel trick because there is no dot product of this format of x1 comma x2 format or phi x1 and x phi of x2 format, whereas the dual form, if you see, has this particular format. So between all pair of points you have to compute these dot products. That's why we very often solve the SVM formulation in the dual form. And for this particular example we were doing 1 plus xi xj whole squared minus 1. So if you think about it, since we said that we are performing this calculation over all pairs of points xi xj, if we do this calculation between all pair of points, we'll end up with a matrix which would, as expected, look fairly similar to a covariance matrix, and this matrix is often called the Gram matrix. For valid kernel functions, this is a positive semi-definite matrix, right? So if you're getting a sense in a very broad sense, this is just telling us about the similarity between these pairs of points. In this case it's not really normalized, so it's not a direct indication of the similarity, but in often cases this you can very easily interpret the matrix to be indicative of the similarity between these pairs of points. Okay, we'll take now another example to better cement our understanding of the kernel function. Now we have original data in R2 and we have again two classes. So I'm not suggesting that we use the kernel function as just the square of the dot product in the original dimension. So you have original vectors, two input vectors x and x prime. You just do a dot product between them, or just do a matrix product, the transpose of the first, and then do a squared, right? So we already know that k of x prime is the same as the dot product of phi of x and phi of x prime. But let's just try and calculate phi of x. Let's try and understand that using this particular kernel function, what is the transformation that we get, or in what space does the kernel function project this data to, right? So we write k of x and x prime as the dot product between these two, or the matrix product between the transpose of the first vector and the second vector. So essentially you'll get x1 prime plus x2 prime the whole squared, right? And all you now need to do is to just expand this out, and if you expand this out, you'll basically get x1 squared x1 prime squared plus x2 squared x2 prime squared plus 2x1 x1 prime x2 prime. And then again we need to break this down as a dot product of two vectors. These vectors are of the format x1 squared root 2 x1 x2 and x2 squared, right? Since the original data was x1 x2, so you have now separated out phi of x and phi of x prime, basically phi of x and phi of x prime, which is what we required. So what this is essentially saying is that we projected the original two-dimensional data to now a three-dimensional data, and we can now visualize this three-dimensional data and get a better understanding of if this kernel will be useful for us or not. Alright, so we have, now let's go back. So you have the original data as x1 x2, so and the transform is x1 squared x2 squared, and the third dimension is root 2 x1 x2. So the original data was x1 equal to 1 and x2 equal to 0. So that gets transformed to the first dimension, which we have is x1 squared, the second dimension is x2 squared, and the third dimension we have is root 2 x1 x2, right? So if we put this point 1 0 on the x1 squared plane, x1, so it is going to lie on this line x1 squared, and it has no projection on the other, along the other different axis. Whereas similarly this point 0 minus 1 and 0 1 will lie on this x2 axis, since it only has the x2 component, and since all the 4 points simultaneously don't have the x1 and the x2 component, the third dimension doesn't really have anything useful. So we can very trivially draw a separating hyperplane like this, right? And then you can very trivially project this hyperplane back to the original dimension, and you can get a sense of how would this classification happen, right? So there are various forms of kernels, but the common ones which are being used is the linear kernel, where the linear kernel is just a dot product of the vectors. Then you can use a polynomial kernel. So in the linear kernel, you're basically not projecting the data to high dimension spaces. And just to put it simply, the unprojected, or the default case for SVMs is the linear kernel, where you don't have to project the data to high dimension. In the polynomial case, you basically take the dot product and then add a scalar p, and then raise this entire thing to a power q. Depending on q, you will get now a different dimensional space. The more the value of q, the higher the dimensional space you're projecting the data to. And the third, and perhaps the most commonly used kernel function, is the Gaussian kernel function, which is of the form e to the power minus gamma and the length of the vector x1 minus x2, or basically the square of the length, right? Where gamma is often written as 1 over 2 sigma squared. In many implementations, in some implementations you give the gamma parameter, in some implementations you give the sigma parameter, and this is also called the radial basis function. And in a minute we'll try and understand why this radial basis function even makes sense. Before that, let's quickly do some exercises to further solidify understanding of projection of SVMs to high dimensional space. So we take an original vector x which contains two dimensions, now x1 and x2. The question is that what space does the kernel x prime, which is 1 plus x prime the whole cube, belong to? So if you remember, I was mentioning that if we vary this q, based on this the dimensionality of the projection will vary. The higher the value of q, the higher the dimensionality. And so we know that the x original data input data belongs to R2. The question is, what space does the kernel or the projected data lie in? Again, for simplicity, we'll assume there are 2 points x and z, and we expand this entire thing out. So we write 1 plus x1 z1 plus x2 z2 the whole cube, right? So x prime basically here means it's a dot product between x and x prime. So we do a dot product between x1 x2 and z1 z2, so that's why we get x1 z1 plus x2 z2, and you take the whole cube of this, and then you again write this in the form of phi of x dot phi of z. So for doing that, we need to look at, so since this is symmetrical in nature in terms of x and z, we can trivially just think about writing this in the form of, just look at all the x terms and see the degrees. So a plus b plus c the whole cube can be written as a cube plus b cube plus c cube plus thrice of a plus b, a plus c, b plus c. So if you expand this entire thing out, you'll see terms of, I'm talking only in terms of now x1, terms of x. You'll see a term of degree 0. You'll see two terms of degree 1, which is x1 and x2. You'll see terms of degree 2 like x1 squared, x2 squared, and then x1, x2. And then you'll see terms of degree 3, which is x1 squared, x2, x1, x2 squared, and x1 cube and x2 cube, right? If you count this total number of dimensions, this is 10. So this should give you a sense that even using a small q of 3, you're now projecting the data to a much more high dimensional space, which is 10. Okay, a similar question: what space does the RBF kernel lie in? And there are various interpretations or various ways to answer this question. I'll take a more mathematically inclined answer in this particular example, and later on we can hopefully discuss this in a more intuitive sense also. So we just expand. We know that E of alpha can be written in this particular format, which is a summation over n from 0 to infinity of alpha raised to power n over n factorial. We can expand it this way. So if you were to expand this kernel function of between k of x and z, it's going to lie in infinite dimensional space. Now this can be hard for you to interpret because thus far everything that we'd been seeing was a high dimensional space, but you could always count that. Now we're talking about infinite dimensions. So this is again something interesting. The kernel function needs to be computable, but the higher projection need not be computable, because now think of it, you cannot really compute this infinite dimensional space, right? But you can compute the kernel, and then you can solve for the SVM. So this is another interesting thing which comes up when you talk about the RBF kernel. We'll gradually try and understand the RBF kernel even more as we'll go ahead. I am going to not discuss about parametric versus non-parametric for now. We'll do this once we have studied KNN, and after that we'll get a much better sense of what is parametric and non-parametric. But I'll just talk about how we used to make predictions and in SVMs, and this will help us better understand what the RBF kernel is allowing us to do. So we know that for a test point x test, we can compute the y hat as the sine of w time x test plus b, and or we can just expand out w to write it in the form of j equal to 1 to n alpha j y j. So previously we had xj dot x test plus b. We can also just replace the dot product with the kernel function if we are projecting this to a high dimensional space. So the alpha j's will all be zeros except for the support vectors, right? So this is not the original data. There's a small typo in the sense that we are not going to be directly using xtest. We'll be doing a transformation to phi of xtest and phi of xj, and that dot product we are replacing with k of xj and xtest. So we know that k of xj and xtest for the RBF kernel is of this format: e to the power minus gamma xj minus xtest. And if we go back and try and understand what exactly is happening, right? So we said that the kernel function in some sense is used to encode the similarity, right? Because it's a dot product in some sense, or it tells you in some cases this number varies between 0 and 1, telling you about the similarity. So let's just for now just consider that this particular function k is a number varying between 0 and 1, which is 1 if xj is fairly similar to xtest or is the same in the vector space, and it's 0 if these two quantities are highly different or they are orthogonal vectors, right? So if we look at y hat of xtest and we expand this out, and let's for now just consider all the support vector examples only. So we look at alpha j, yj and this function, right? So if x test is the same as a particular, is very similar to another xj which we already know. So this is in some sense suggesting that that basically that the sign that you'll be giving or the prediction that you'll be making would be fairly similar to the xj. And if x test is very far or very dissimilar from a given xj, then this entire terms will become 0, and thus this particular alpha j yj will not account for this or will not be counted for making the prediction for this example. So in essence what we're trying to say is that whenever x test is close to an xj, only those values would be useful for predicting the class for a particular example, right? Or the degree that to which you're similar, to degree to which x test is similar to xj, to that degree that particular xj will contribute towards the prediction, right? So in some sense now what we're trying to predict or y hat of x test is now depending on all the examples. In this particular, in the strict sense, alpha j's would be zeros for all the non-support vector points, but in general, what in some sense we are looking at all the trained points, right? So that's where the definition of non-parametric also comes into play, but I'm not going to go into that for now. But the essential idea that we've been seeing is that closer the x test is to xj, the more xj is influencing x test, and thus the hypothesis, right? They We can also interpret the RBF kernel from a mathematical viewpoint. So we've written that y hat of x is the sign of summation alpha I yi e to the power minus xi, and the summation is over I plus b. Now let's look at the different components of this. We have this, the length of this vector x minus xi, which corresponds to the radial term. So since this is similar to how you would define radius, right? If this thing is a constant, then you're defining a circle with a specific center. The second component alpha yi is the activation component. So if alpha is are 0, then irrespective of how close or how dissimilar these points are, this particular term will not contribute to the prediction, right? So basically you're saying that the activation is absent in this case. So while this and the final term is the basis. So you can think of in terms of there is an activation and there is a basis. So you think of there are multiple basis vectors and each of them is contributing to some extent. That contribution is quantified using the activation. So that's why you get the radial basis function. The gamma parameter tells us about the influence of a single training example on the predictions, right? So if we look at a single training example xj and we look at any test point x or any point x, if the gamma value is low, so we need to look at the functional form again, right? The functional form is e to the power minus gamma x minus z whole square, right? If gamma is low, if gamma is low, then there is a high influence of xj, as in, so then if we compute this function, kernel function, between xj and x, then it would be a very smooth and a widespread function. You should just try to plot this in your own time and you'll be able to verify this. But if gamma is high, the higher the gamma you put, the more pointed this surface looks like, which means that the influence of a point xj or a training point xj in this case is really small. It does not extend to a large boundary or a large enough region. Again, as and when we see some examples and we write some code to use to vary the values of gamma, we'll be able to understand this even better. And finally, before we end today's lecture, I'll go through an excellent resource, which is this book by Jake Vanderplas called Python Data Science Handbook, and it has a very interesting chapter on support vector machines. So this is I'll through this notebook I'll also go through and revise all of the things that we've studied thus far in support vector machines. We said that there are these two classes of points. We could separate them using multiple lines or multiple hyperplanes. We end up choosing this particular hyperplane because it maximizes the margin, and so these are all showing the margins. And if you see this particular one going from, yeah, this particular one shows the maximum margin, the others have thinner margin, thus we would be picking up this particular decision surface, decision boundary. Once we do that, we'll get a few points which are known as the support vectors. Now these are the only points which are actually required to support the entire classification. Like even if this point goes missing, this the SVM learned would be exactly the same, and that's exactly what they do next. So they end up showing that, first they just use some 60 examples to learn a classification boundary. Then they show that, let's say if they were to add more points, you see more points are added over here and more points are added over here, but the decision surface remains exactly the same, because that's the fundamental properties of SVM, that you require uh, only the support vectors, and the support vectors are the only things or the only vectors which are supporting the entire classification. None of these points are impacting because they're far away from the margin, right? So again, thinking in terms of the constraint optimization perspective, none of these points, the multipliers for them will all be zero, because none of these points are actively changing the constraint. They're not actively participating in the constraint optimization. That's adding or deleting any of these points is not making any difference to us. And then in today's lecture, we saw that there are many cases in which linear classification will not work. The one way to do that is to project the data to high dimensional space, and that's exactly what they've done in this example. And now you can think about drawing a hyperplane to trivially separate these, and you can then project the hyperplane back into the lower dimensional space, and then you'll again get a few support vectors. Again, these points which are further away are not really critical. I am not going to be talking about soft margin classifiers today. We'll do that in the next lecture. So we'll now stop this current lecture. In the next lecture, we'll discuss about the case. The case is like this, right, where you cannot clearly separate out this data in a linear sense. The idea is that can we allow some relaxations to the constraint that we had. So with that, we'll stop today's lecture.